Okay. Ever tried making something like sourdough or maybe kombucha at home?
Oh yeah, they can be tricky.
Right. It feels so alive, almost temperamental. You change one tiny thing, temperature, maybe an ingredient, and poof.
It throws everything off, that feeling, that sensitivity. It's actually key in so many natural processes,
Like fermentation.
exactly like fermentation. Crucial for tons of foods we eat every day.
Yeah.
And getting the conditions just right is, well, non-negotiable.
Which is precisely why we're doing this deep dive today. We're looking at a source called Calculus and Fermentation pH Control.
Sounds technical, but the idea is fascinating.
It is. Our mission, really, is to unpack this link the source highlights. It connects differentiation, the calculus concept directly to food security
How so?
through understanding pH sensitivity and fermentation.
Ah, okay. Because that pH level is so critical. If it drifts, even a little bit,
It's not just about taste, is it?
not at all. It affects how well the good microbes work. It can let bad bacteria grow. And that messes with safety, consistency.
Which brings us straight back to food security, making sure food is reliably safe.
Absolutely.
And this is especially relevant if you, the listener, are maybe studying differentiation or integration right now.
Right. Because this shows it's not just abstract math. These are real tools for understanding the sensitive world around us.
That precision you mentioned, too much acid, too little.
The whole batch could be ruined.
Yeah.
Imagine that on an industrial scale. Big problem.
So this is where it gets really cool. Differentiation. What is it at its core?
It's about change, right? Specifically, the instantaneous rate of change.
Instantaneous.
Yeah. Like how much is one thing changing right this second if you nudge something else just a tiny bit?
Okay, give me an analogy.
Think about driving. Differentiation isn't just your average speed change over a minute. It's the exact rate your speed picks up the moment you press the gas a bit harder.
Or slows down when you tap the brake.
Exactly. How sensitive is your speed to that tiny foot movement right now?
Got it. So applying that to fermentation pH differentiation lets scientists figure out precisely how sensitive the whole process is.
Yes, to those tiny shifts in acidity or alkalinity
Mm-hmm.
at any specific moment.
And why is that so crucial? Can't you just sort of, keep it in a general range?
Well, biological systems often aren't linear. A small pH change here might do almost nothing,
Okay.
but the same small change at a slightly different pH level, it could make the microbe suddenly stop working or go way too fast.
So it finds the danger zones.
It helps pinpoint those critical points, yeah.
Yeah.
And it measures the exact strength of the sensitivity there.
So it's not just, pH is rising, maybe things change.
Right, it's knowing, okay, we're at this pH. If it goes up by just 0.1, the reaction rate will drop by exactly this much per minute.
Wow. That specific instantaneous measure of sensitivity that comes from differentiation.
That's what it gives you. And that knowledge is incredibly powerful for control.
How so? What do you do with that knowledge?
You use it to build smart control systems, systems that know about this sensitivity.
And they can react.
They can make tiny, really precise adjustments.
Yeah.
Add a bit of buffer, maybe tweak the temperature slightly, just enough to counteract any unwanted drift.
Keeping the fermentation in that perfect, safe, optimal zone.
Exactly. It's the math enabling reliable food production, robust systems.
So when you think about it, calculus is quietly helping make sure the yogurt, the bread, all that fermented stuff, it's consistently safe and tastes right.
It's a key player, a silent partner maybe, in putting food on our tables, maintaining food security. It gives that deep insight needed for managing sensitive, variable systems.
Okay, let's wrap this up. The big takeaway from our deep dive really is that something seemingly abstract like differentiation, it's actually a vital practical tool.
For understanding sensitivity in really important real-world processes, like making food safely.
And for you, maybe learning this math right now, it's a pretty powerful example, isn't it? Shows how these concepts get applied to solve tangible, complex problems.
Definitely. It's not just theory.
So here's something to chew on. Think about that incredible precision needed for fermentation. Controlling something alive, complex, it needs sharp tools to measure its sensitivity. Where else might the math you're learning be doing that same job? Quietly making sense of sensitivity, letting complex things work reliably just behind the scenes.